So I think we are streaming, right? Live on
Just
YouTube.
1 second, just 1 second. I'll update you as soon as we are live actually. So we are live now, sir.
Okay.
So Dr. Aneba, we can formally start now.
Yeah.
Thank you.
Thank you, Kamal sir, for all the support. So I welcome you all to this webinar. So it is on black holes, and it will be mostly focusing on the Nobel Prize in Physics in 2020. So our today's speaker is Professor Mikhail S. Volkov. So he is working right now as a professor of physics, University of Tours, France, from 2002. So before that, he held the postdoc positions from University of Zurich, Switzerland, University of Jena, and a research associate position at University of Tours. So Professor Volkov mainly works on the theory of general relativity with Young-Mills field, along with the Einstein equation, which provides the first explicit counterexample for no-hair conjecture of black holes. So he also works on the theory of non-abelian supergravity monopoles, Euclidean quantum gravity, and field theory, especially on the resonant excitations of 't Hooft-Polyakov monopoles. So by that, I think we can start. But before starting, so I'll welcome Honorable Vice Chancellor Sir of Schulen University to say a few words before we formally start. Khosla sir.
Oh, thank you very much, Anarvan. It's my pleasure to welcome Professor Mikhail Volkov for this webinar, which he has kindly consented to be with us. I'm thankful to him on behalf of the university. Professor Mikhail, we are a small specialized research-based university in India, located in the mid-hills of Himalayas, lot of vegetation and biodiversity and rich resources. We were established in 2009. In the last 11 years, we have made rapid strides as a new university. And we in India, we are known today as a research-based university. We have a lot of research with the different faculties, Faculty of Basic Sciences, Faculty of Biotechnology, Faculty of Pharmaceutical Sciences, Faculty of Engineering and Technology, Faculty of Agriculture, and Faculty of Business Management. Particularly in research, we are figuring among the best institute in the country and also 14th best in the Asia during the current world ranking Asia 2020. So we are very honored that you have agreed to be with us and speak to our students. We all will be benefited by your concept of black holes. It's not physics is not my subject, but black holes, like any other scientist, I have also interest. So I will be listening to your lecture attentively to learn actually what are black holes, how these are caused, what changes have taken place over the different years in our concept of the black holes. Thank you very much. I wish you all the best, and especially again that you have agreed to address our students. Thank you very much.
Thank you, Khosla sir, Professor Khosla. So I think we can start now because Professor Volkov, please start now. Okay.
Okay. Thank you for inviting me, and thank you for giving nice introduction. Thank you for presenting me. So it's indeed I've been studying black holes more or less all my life, and today, I will try to explain why they have given Nobel Prize for black holes and what are black holes. And I understand that I understand the students probably don't know general relativity, but I assume that they know at least special relativity. I will try to explain basic concepts of general relativity, and then the applications like such as solution, gravitational collapse, and etc., and so on. When people talk about black holes, so if you read magazines, newspapers, then you can see pictures like that. People usually imagine something like this. So black holes are, in a sense, a hole in space. Well, this is clear, but what is not very clear is how to make a hole in empty space, because empty space is already empty. How can you do a hole in something which is already empty? But the answer is basically that in general relativity, the space, even if it's completely empty, still has a property, something like elasticity, and it can be deformed and bent, curved, and the black hole is the extreme example of such a deformation. So this is a deformation of empty space, and then in a sense one can fall inside, and then this the black hole will swallow you. So this is what more or less everybody knows. But before going to general relativity, let us now see what happens in classical Newtonian gravity. Let me remind you the basic equations of Newtonian gravity. Newtonian gravity operates with a gravitational potential phi, which fulfills the Poisson equation. So phi is generated by rho, which is the distribution of mass density, and it fulfills the equation, Laplace equation, so Poisson equation. So there is a Laplace phi is 4 pi g rho, where g is a gravitational constant, Newton's constant. And when you solve this equation and find the potential phi, then the minus gradient of phi determines the acceleration of free fall. And this acceleration is the same for all bodies, because it doesn't depend on the mass of falling bodies. As an example, one can take, for example, a point-like mass distribution, just a mass located in the center of coordinate system. Then, when you solve equation, the Poisson equation, you find the following solution for the Newton's potential, and this gives you the following acceleration. And so this acceleration is directed towards the center, the mass, and so which means that the gravity is an attracting force. Now, let us consider the following example. Suppose that we have our planet Earth, which has size r, mass m, and there is an object which is at rest at the Earth's surface. And then the energy, total energy of this object is the potential energy in the gravitational field, is given by this expression, and it is negative. Now, suppose that we want to launch in space this object. Suppose that this object is a rocket. We wanted to escape from the Earth attraction. And in order to escape, the total energy of our rocket should be non-negative, should be either 0 or positive. And therefore, the rocket has to be given a kinetic energy, mv squared over 2. And since this should be positive, this gives the following bound for the escape velocity. So this is called the cosmic speed. Now, so this is the cosmic speed is for our planet. This is something like 11 kilometers per second. Now, consider the following thought experiment. Suppose that the mass of the Earth is kept constant, but we start compressing the Earth, thereby reducing its size. So radius r. And in this way, the escape velocity we will increase, and it will increase more and more until it reaches the value of the speed of light, if the radius r is given by the following value. And this is what is called in general relativity Schwarzschild radius. If the radius of our planet, if the planet is compressed even more, then the escape velocity becomes bigger than speed of light, and therefore nothing will be able to escape, because nothing can move faster than light. Amazingly, these non-relativistic considerations give exactly this, the correct value for the Schwarzschild radius. So in other words, the very concept of black hole, which means the place from where nothing can escape, exists already in classical Newtonian mechanics. The only problem is that in classical Newtonian mechanics, there is no limit in speed. The Newtonian mechanics doesn't know that the speed of light is the maximal speed. So this fact only arises in the context of relativity theory. Now let's come to the relativity. The theory of general relativity, this is the theory of gravity, invented by Einstein in 1915. This theory uses the following basic concept. It considers gravity as the curvature of space-time geometry. So I think the best analogy is shown here. So imagine a rubber, a surface made of rubber. If this surface is flat, then the lines of shortest distance are just straight lines. But if you put something on the surface becomes curved, and in order to get from point A to point B along the shortest line, you should not take the straight line. So you have to follow a curved line, and therefore, the curvature is interpreted as a attraction of gravity. So this is the main idea. And so the theory was, as I said, proposed more than a century ago, and almost immediately it was confirmed partly. So some of the predictions, some of the simplest predictions, like light bending and advance of Mercury perihelion, were confirmed immediately. Whereas other striking predictions, as for example, the existence of gravitational waves, black holes, were waiting for almost a century until now, and only now they start being confirmed. And we are living this spectacular period because 4 Nobel Prizes for gravity research were awarded over the last 10 years. 4. This is incredible. And so our subject is of today is the last Nobel Prize of this year. Now, let me go into details a little bit. So what does it mean, space-time geometry? So since people know special relativity, let's consider first the case where there is no gravity. If there is no matter, and then the space-time is empty, then it should be flat Minkowski space. And well, I assume that the people know what Minkowski space is. This is a 4-dimensional space with whose 3 coordinates are usual x, y, and z. And the 4th coordinate, or rather coordinate number 0, this is the time. or more exactly, speed of light multiplied by time. And then the space is the geometric properties of this space, or space-time rather, are determined by the structure of the interval. So the interval, or the distance between points A and B, is computed by using the following rules. And so one takes the difference of squares, squares of differences of coordinates, and 3 times with plus and once with minus sign, which means that the distance in Minkowski space can be positive or negative or 0. And in particular, if the distance between points is 0, this doesn't mean that the points coincide. This means that they're related by a space, by light-like interval. Now, if points are very close to each other, then the difference of their coordinates is very small, infinitesimal. Then the expression for the interval becomes this. And if you call CT x0, and if you call XYZ correspondingly x1, x2, x3, then the interval can be written in the following way, or equivalently as the following quadratic form, whose coefficients form a matrix or a tensor called Minkowski metric. This is a symmetric matrix 4 by 4 with the diagonal elements -1, 1, 1, 1. And this, I suppose, everybody knows. Now,
yes, they actually know. Okay, so special relativity is a part of the physics curriculum.
Okay,
so they know. Okay,
very good, very good.
Hmm.
Now, if there are no other forces, for example, if there are no electromagnetic forces, etc., then the three bodies in Minkowski space follow straight lines. So they are described by the following equation. The second derivative of coordinates with respect to parameter along the line is 0. And the solution of this equation is this, where v mu and x0 mu are integration constants. And in particular, v mu is a tangent vector to our straight line. And the tangent vector can have a norm. The norm of the vector is defined as a product of the vector with itself. So this is the norm. The norm can be either negative or positive or 0. And so if the norm is negative, then the line is called time-like. And this corresponds to a space-time trajectory over ordinary objects, like just heavy bodies. So let me rather go to the next slide. No. First, let me finish. So if the norm is 0, then it is the trajectory of light, and if the norm is positive, then it is space-like line describing trajectory of an object moving faster than light. So such objects probably do not exist, but still mathematically one can discuss the possibility. And then from the geometrical viewpoints, it is convenient to introduce the null cone or light cone. So this is the cone where all light isotropic lines are located. All time-like lines are inside. For example, the trajectory of an object which doesn't move, which rests at a given space point, is just the timeline, because any object moves along time. And finally, so if the object moves but slower than light, then it follows this brown line. And if it moves faster than light, it goes outside the light cone. So these are the basic facts. And finally, what I'd like to say is that in Minkowski space, one can, there is no need to use always the coordinates x, y, z. One can use any other coordinate system. In particular, one can, for example, use spherical coordinates r, theta, and phi. And then the line element assumes this form, and it can be represented as a contraction of the metric G mu. And then the G mu is always Minkowski tensor, Minkowski metric, but written in spherical coordinates. So it's the same, the tensor, although it looks different. And this difference can be removed by changing back coordinates. So now this is a special relativity. Now, what is general relativity? It is basically the same thing. The only difference is that G mu, the tensor which determines the distance between points, is now more general. It is just any matrix which can be locally at any given point transformed to the Minkowski form, but only locally. So this possibility of transformation in the vicinity of each point is called equivalence principle, which means the possibility to locally exclude gravity by passing to a freely falling frame. But globally, it's not possible. Globally, it is just a matrix whose components are 10 functions, because it's symmetric matrix. So there are 10 independent components, 10 functions of 4 coordinates. And this is the central object of general relativity, the metric. So everything is determined by the metric. So just for information, I quickly mentioned the formulas. The metric is used to construct so-called Christoffel symbols, where G, alpha, beta with upper indices is the inverse matrix. And then using the Christoffel symbols, one constructs so-called Riemann tensor, and whose contractions are so-called Ricci tensor and Ricci scalar. And finally, they are used to define so-called Einstein tensor. And the Riemann tensor is distinguished by the following property: if it is 0, then the space-time is flat, even though the metric can look different, but space-time is Minkowski. If the Riemann tensor is not 0, then the space-time is generally curved, and so metric cannot be brought to Minkowski form by any transformation, global, I mean. Now, suppose that metric is given. The metric determines the geometry, and it encodes in it the effect of the gravitational field. And this effect manifests itself in the following way. So first of all, one can consider curves in space-time. They're also described by some function x mu of lambda. And then the tangent vector to every curve is defined as before, as in special relativity. And the norm is also defined as before. And then also, depending on the sign value of the norm, the curve can be time-like, lying inside the light cone if the norm is negative. They can be light-like, so if the norm is 0, or they are space-like if the norm is positive. These are curves, just arbitrary mathematical curves. But what about trajectories of physical bodies? These are special curves called geodesics. These are curves of minimal distance. So curves whose distance between two given points A and B is minimal. And these curves are the solutions of the following system of differential equations called geodesic equations. And the effect of gravity is encoded here. For example, our planet Earth, which orbits the Sun, follows the trajectory. So because it moves in space and in time. And this trajectory is precisely the solution of this system of differential equations, where gamma depends on the metric, and the metric depends on the mass of the Sun. So therefore this gamma and the metric, they encode all information about gravity force. Now, suppose that the gravity is weak, is very weak. Then the metric should be close to Minkowski metric, and it can be represented in the following form. It is almost Minkowski apart from the function phi. If phi is 0, then it becomes precisely Minkowski. And here there is a phi divided by speed of light squared. And the speed of light is a very large quantity. And phi turns out to be precisely the Newtonian potential, which we described before. And then the geodesic equation in this metric assumes the form of a standard Newton's equation plus small corrections. And small because the ratio of phi over c squared is small. And these small corrections in the geodesic equations describe the essential effects of general relativity, which can be observed inside solar system. Because inside solar system, the gravity is weak. So the gravity, the essential gravity force is produced by sun. Sun is heavy, but not heavy enough for the relativistic effects of gravity to be really important. So they are weak, but still they're measurable. And these are three classical tests of general relativity. These are shift of mercury perihelion and bending of light in the sun vicinity. So let me show you the picture. So in fact, in classical Newtonian mechanics, the orbits of all planets are elliptic, and then they're closed. So these are just closed ellipses. Whereas in general relativity, they are no longer closed. They are, strictly speaking, no longer ellipses. And so the perihelium moves after each revolution. And this effect is maximal for Mercury, because Mercury is closest to the sun planet. And it was measured, it was actually, the shift of perihelium was actually measured. I think it was in 1917, because immediately after discovery of general relativity, this prediction was confirmed immediately. Then another effect is the bending of light. So in Newtonian gravity, the light propagates along straight lines, whereas in general relativity, when light passes in the vicinity of a massive body like sun, it deviates. And therefore, when we see when we observe a distant star, and we see that the position of this star moves a little bit. So if the star is in the sky is close to the edge of the sun, one can see that it displaces slightly. And this is again a measurable effect. This was measured in 1919, during the sun eclipse. So this was a second confirmation of general relativity. And then the third one is this. Suppose that an observer is at rest at some space point, for example, at point x0, y0, z0. Then it's the time he measures is not the same as the coordinate time measured by distant observer at infinity, because his time is defined as the negative value of the interval, and it is this one. And since the gravitational potential phi is negative, the interval over proper time is less than the interval of coordinate time. In other words, the time in gravitational field runs slower. So there is a time deceleration. And so if you go to the region where the gravity field is strong, then your time will go slower, and so you will remain younger. You will be younger than those people who are far away. And so this is another version of twin paradox. So if you approach the region of a very strong gravity field, and when you get back to Earth, you will discover that the people are older than you. And this is this manifests itself usually as the redshift. So suppose that there is, for example, the sun, where the gravity potential is strong, and it emits a light, and the frequency of light is determined as time interval between two maxima of the wave. And then this time interval is less than the interval, time interval at infinity. Therefore, the light, the blue light emitted in the region of strong gravity field arrives to the asymptotic region of zero gravity redshifted. So the observed light will be redder than the emitted light, and this can be observed as a shift of spectral lines. So it's enough to measure with high precision the position of lines of chemical elements in the spectrum, to see that they are not the same as the positions of lines measured in the lab. So they are redshifted, and so therefore, when we measure spectra of light arriving from distant stars, we can deduce some information about the force of gravity at the surface of the stars. Okay. And so this is all about the general information about general relativity, about curved space. Now let us consider a concrete example of curved space. Let's take again the flat Minkowski metric, and let us introduce here a function a of t. And then with this modification, the geometry is no longer flat, and it describes the expanded universe, our universe where we live. And the function is the size of the universe, and it grows in time. And therefore, the physical distance between points in our universe increases in time, even if the points do not move. There is a good analogy. Suppose that you take a balloon, rubber balloon, and with the pencil, you draw 2 points at the surface of the balloon, and then you start inflating the balloon. The points do not move because they are drawn. But since the radius of the balloon will be increasing, the distance between the points will be getting bigger and bigger. So this is the analogy. Now, what determines the function A? The function A is determined by the Einstein equations. And then in this particular case, the Einstein equation is there is only one, this one. And where on the right, there is rho. And the rho is the average density of mass filling our universe. And nowadays, we know that the rho is more or less constant. It contains the contribution of matter, which is roughly about of the usual matter, which is makes only about 5%. Of dark matter, which is about 25%, and then the rest is a constant called dark energy. And if you assume that this rho is roughly constant, then this equation tells you that the A should be increasing as exponent of time. And this fact was measured. This was measured by observing the spectra of the distant supernova. And so it was directly discovered that our universe indeed is inflating, not just expanding, but inflating, which means that expanding with acceleration. And this fact implies, one has to go in the other direction, implies that the rho must be constant, and this implies that there must be the dark energy. And these facts, they lead to the Nobel Prize for this discovery. It was 9 years ago. So exactly the Nobel Prize for discovery of accelerated expansion of our universe. And so this expansion again is detected by direct observation, but then the Einstein equation imply that the origin of this expansion must be a constant value of rho, which means the presence of a mysterious, invisible matter component, which is actually dominant in our universe. Dominant. 70% is more than 70% is in the dark energy form. It's a dominant, and nobody knows what it is. This is the one of the main puzzles of the modern theoretical physics. Now, this is a particular example. Let's ask the question: what determines the metric in general? In general, the space-time metric is a solution of a set of second-order nonlinear partial differential equations called Einstein equations. So here, on the right, there is a combination G mu this Einstein tensor, which I showed before, which is constructed from the metric and its second derivatives. And on the left, there is a thing which is called energy momentum tensor. And this is a matrix which encodes information about the distribution of matter. In particular, its components are the matter energy density and pressures. So in the simplest case, for a gas, a fluid, T mu is this. And schematically, Einstein equations can be written in the following form. There's a hyperbolic system. There is something like D'Alembert operator, part acting on the metric. On the left and on the right, we have the energy momentum tensor. And in fact, if the gravity is weak, if space-time metric G mu is very close to Minkowski metric, is Minkowski metric plus small correction, then the Einstein equations reduced to wave equation for these corrections. We have the box usual D'Alembert operator of H mu plus nonlinear corrections, and this is equal to the source. And these equations describe gravitational waves generated by time-dependent matter sources. For example, if there is something changes in time, some collision of stars, some pulsations, this should produce gravity waves. And this was known already to Einstein immediately after discovery of his theory, but it took a century until these waves were actually detected. The problem is that they're extremely weak. They are generated somewhere far away in space, millions of light years or millions of light years away. And when they arrive to us, they're very, very weak. And then one has to use a really special equipment in order to detect them. And this was done for the first time 5 years ago. And the Nobel Prize was given for this 3 years ago. Okay. And now let's come closer to the subject of our talk, to black holes. So black holes were first discovered by Schwarzschild. Karl Schwarzschild was a German physicist who discovered first exact solution of Einstein equations only 3 months after the equations were published. Here he was serving in the German army during the First World War, and he was killed several months later. But he had enough time to publish his solution. And so the idea is this. So this is a solution which describes a gravity field of a static star. What is a star? Star is a ball of gas, of hot gas, characterized by certain matter density and pressure. And let's assume, for simplicity, that the matter density is constant inside the star. It's not true, but let's assume. That the star has a radius r. Oops, something happened. Sorry. Well, okay. That the star has a radius r large, and the constant density rho, which is zero outside and constant inside. And if you solve Newton's equations, and then in addition, one has to add the pressure, because without pressure, the matter would just fall on the center. One has to add the pressure to compensate the gravity force. So there are two variables, phi, gravity potential, and the pressure. And when we solve the Poisson equation, we obtain the following solution. That there is a standard Newton potential outside, the pressure is zero outside, whereas inside the star, there is something like this, some values, some regular values for phi and for the pressure. And then the pressure adjusted in such a way that it's always finite, but vanishes exactly at the star surface. Now, what Schwarzschild did was the following. He took the following metric, static and spherically symmetric metric, which contains two functions of r, a and b. If these functions vanish, then this is Minkowski space, no gravity. But then Schwarzschild solved the Einstein equations inside the star and outside the star, and matched the solution at the surface, and he obtained the following result. He obtained that outside the star, where pressure is zero and rho is zero, the functions a and b are given by the following expression. where Rg is the Schwarzschild radius. It's exactly the same value that we discussed in Newtonian theory. Inside there are some functions. And now it was unclear to Schwarzschild what this means. This Rg, because something is clearly happens where R becomes equal to Rg because these functions vanish. Well, he thought that maybe this regime is never achieved, because for physical stars, R large is much bigger than Schwarzschild radius. But still, he thought that maybe this Rg is the minimal value of the size a gravitating body can have. And in fact, his solution also shows his interior solution shows that if we keep the mass constant and decrease R, then the pressure at the center increases faster and faster and finally diverges a bit before the Schwarzschild value is achieved. So therefore, star cannot be too small. Okay, this was observation, but he thought, Schwarzschild himself, that it was okay, just observation. Why should one care? Because for physical stars, this regime is not achieved. And let's see what happens for physical stars. For example, our sun. Our sun is a ball of the radius of roughly 1 million kilometers, whereas the Schwarzschild radius is about only 3 kilometers, which is clearly much less than 1 million kilometers, and so one can forget about this. However, there is a catch here. Our star, our sun, any star, is a complex object made mainly of heavy gas, and then this is enormous mass of gas which gravitates and which wants to contract gravitationally, but it doesn't happen because at the center of the star, the pressure is so high and the temperature is so high that the hydrogen starts to burn. So there is a fusion reaction happening at the center. So the fusion of hydrogen atoms into helium atoms, and then the energy released during this fusion keeps high the temperature, and then the high temperature means high pressure. And so this is the pressure which provides resistance against the contraction. Now, this is okay, but then the question, how long will this situation continue? Our sun exists already for roughly 5 billion years. It can go on for maybe other 5 billion, but then sooner or later, the hydrogen will be over. There will be no more hydrogen at the center, and so therefore the reaction will stop. If the reaction stops, then nothing burns in this case, and then there is no temperature to support high pressure. What will happen? For our sun, the answer is this: nothing special. In fact, even if nothing burns, then there is a quantum mechanical force, which will be able to stop the contraction. And this is the force explained by the Fermi exclusion principle. The point is that in the center of star, the gas is ionized. It's a plasma made of hot protons and electrons. And then the electrons are fermions. And as everybody knows, fermions cannot be put into the same quantum state, and they attract each other. And this attraction is so high and produce such a high pressure that the pressure high enough to stop the gravitation, to resist the gravity contraction, and therefore our sun will end up in the state of white dwarf. White dwarf. This is the star where nothing burns. It's maybe still hot, but it will be gradually get colder and colder. And this is the typically this is the star of the size of our Earth, and with a very high density, the density of about a ton per square centimeter. And then the closest to us white dwarf is a Sirius B. The point is that the Sirius star is a double star. It has an invisible component, and this component is white dwarf. It's okay, but then the problem is that the white dwarfs, the mechanism which ensures their existence, only works until the upper limit of their mass, and this limit is roughly 1.4 solar masses, as discovered by Indian physicist Subramanian Chandrasekhar, who got the Nobel Prize in 1983 for the structure of stars. So if the mass is higher than this, then the degenerate electron gas pressure is not enough. So it cannot ensure the stability of star. So the star will have to contact. But still, if it's not very heavy, not too heavy, so if its mass falls into this range, where the upper limit is called Tolman-Oppenheimer-Volkoff limit, then something else happens. In fact, there will be the following reaction in the star. So the electrons will be merging with protons to form neutrons, and then the whole volume of the star will be converted to neutrons, and then the contraction will be stopped by the pressure of degenerate neutron gas, which is higher. And this leads to a formation of neutron star. Neutron stars are actually detected, and then they are very strange objects. So they have the size of about 10 kilometers and with an incredible pressure, like 100 million tons in cubic centimeter. And then they're very compact. The ratio of their size to the Schwarzschild radius is above 10. But if the mass, if the star is still higher than this upper limit, what happens? Then there is no force in nature which would be able to resist gravitational contraction, and then the star starts shrinking indefinitely till zero. So it shrinks till its surface crosses the Schwarzschild radius, and then it shrinks until it shrinks to a point where all its mass will be contained, and then the density will be infinite, and this creates a space-time singularity. And in fact, there are exact solutions of Einstein equations which describe this process. And when everything drops to the central point, the result will be described by the Schwarzschild metric in the simplest case, where now R changes from 0 to infinity. And then in this case, the position of the zero, which arises here, should be seriously considered. And then the region inside for smaller values of R is called black hole, because nothing can escape from this region. This can be understood with the geodesic equation, but in fact there is simple analogy. Simple analogy with a waterfall. Very simple. So imagine a river which flows with a speed v large, v capital. and a motorboat whose engine is able to develop a speed v small. Then when the boat goes down the river, it goes with this speed v plus v, and up the river with v minus v. Now suppose that the boat is approaching a waterfall, and then the v large becomes larger and larger until this difference becomes negative. And in this case, both down the river and up the river become down the river. Then the boat will be unable to go up the river. It will be carried by the stream down the river. And this is the same what happens inside the black hole. So if you take a light emitted either inside the black hole or outside the black hole, it always ends up inside. Inside. Whereas the horizon itself, suppose that if you, in fact, this vanishing of this function turns out to be nothing but a coordinate problem. One can change coordinates in such a way that this zero disappears. And in fact, if somebody falls inside, then this person will not experience any problem when crossing the horizon. But when it actually arrives to the center, there will be problem. And so this is it's not very visible, but this is the picture of the gravitational collapse. So this is the surface of the star shrinking to the singularity, and here is the horizon appearing. So all of this was known already in the, I think, in the 30s of the last century. However, people didn't really believe in black holes for the following reason, because this exact solution was obtained on the assumption of spherical symmetry. Otherwise, it's very difficult to solve Einstein equations. However, this assumption could be dangerous because, of course, if the symmetry is spherical, then all matter points arrive at the center. But suppose that the collapse is not spherical. Therefore, they have a random velocity, and then they do not arrive exactly at the center. They miss the center, and then therefore the resulting density will not be infinite. It will only be finite. And it was not clear at all if, under these conditions, the black hole will form. It's a difficult question. To solve Einstein equations without this spherical symmetry assumption is impossible, at least analytically. And then the solution of this problem cost the half of the Nobel Prize in physics. So this half of the Nobel Prize was awarded for the singularity theorem to the British mathematician, not a physicist, I emphasize, not a physicist, a mathematician, Roger Penrose. And he proved the first singularity theorem. He was interested, he was a mathematician, but he was interested in the structure, in mathematical structure of general relativity. And since he had a background completely different from physical background, he applied methods which physicists didn't know. In particular, he used the equations of Indian physicist Rachaudhuri, describing congruences of null geodesics. And his aim was to show that these geodesics develop acoustics. And in fact, he was able to show, he proved the theorem, which shows that it's enough to form a trapped surface. Trapped surface is a closed to surface whose light-like normals, light-like geodesics, normal geodesics, all propagate inside. not inside and outside, but only inside, as inside the horizon. And to create such a surface costs only finite energy density. Infinity is not necessary. So it's only finite amount is needed. And this finite amount of energy density, I need about 5, maybe 10 more minutes. Is it okay? For
Yes.
yeah, okay.
Go ahead, please.
So the trapped surfaces generically arise, and once they appear, Penrose has shown that then the subsequent evolution inevitably leads to the appearance of space-time singularity, which means to the gravitational collapse. In other words, this purely mathematical theorem of Penrose, for the first time, has proven rigorously that heavy enough black stars indeed do collapse, and so end up in a black hole stage. And then there should be, therefore, there should be lots of black holes around, a lot. And here is Penrose, and talking about him, it's impossible not to mention another remarkable person, his colleague and close collaborator Stephen Hawking, who also merited fully the Nobel Prize, but unfortunately he died a couple of years ago. So Hawking was younger than Penrose, more than 10 years younger, and he joined this activity, singularity theorem activity, a couple of years later after Penrose. But then the collaboration was extremely fruitful, and they largely extended and generalized the original theorem, in particular generalized to the case of the initial space-time singularity. And in the community, the theorems are actually known under the names of Hawking-Penrose. And then Hawking did everything in order to make the thing largely accessible. He wrote a book, famous book about the global structure of space-time. And so, because Penrose is a mathematician, he was interested in other things, whereas Hawking only worked on black holes. And in fact, the black holes are largely popular, I think, because of him. And I think the very idea to attribute the Nobel Prize for black holes, I think, is due to him. And of course, you may know that he was a very extraordinary personality, and then he most of his life he spent in a wheelchair or finally in bed. He was paralyzed, crippled. His body he couldn't speak, couldn't move. He could move only one finger, and with one finger he was typing on a special device, typing texts of his articles, and he made all calculations in his head. And then he also typed the words to pronounce in order to communicate with the outside people and in order to give talks. And he was traveling all around the world, and he was and he was the head of department in Cambridge, and even was responsible for all financial activity. Everything, and of course, he made other important contributions to black holes. And particularly, he discovered so-called evaporation of black holes. And now the point is this: okay, black holes are formed, but how to make sure that they're around? How to see them? How to actually feel them? They're invisible. One cannot see them. The point number one, Hawking has shown that they are, even though they do not emit anything classically, they emit quantum mechanically as black bodies with this temperature. This is a fundamental fact, even though it doesn't help much to in order to observe them, since the value of temperature is very small. However, there is an indirect mechanism to observe them, and it's based on the following fact. The black holes, they are absorbing matter. And suppose that there is a black hole which is moving in space, and it meets a cloud of matter. For example, suppose that there is a double companion where there is ordinary star and a black hole. And then the black hole will be sucking inside the gas, and then the gas will be falling inside, and when it falls inside, it accelerates till relativistic velocities, and then it starts to emit electromagnetic radiation, and then the emission rate can be enormous. So these waves range from radio waves to hard gamma rays. And the extreme example of this process is provided by quasars, which are the most luminous objects in universe. And so this is a picture. This is real data of Hubble telescopes. Quasars are supermassive black holes with a mass of the order of billion of solar mass, which live in galactic centers of galaxies. Now, it's believed nowadays that almost every galaxy contains in its center a supermassive black holes, but not all of them are quasars. So they become quasars only if they're surrounded by matter, and then this produces gigantic luminosity. But this luminosity can oscillate within hours only, which means that the size of the region from where the radiation comes from is only of order of several hours. And this is precisely the size of the event horizon. Moreover, quite recently, 2 years ago, they managed to actually see the black hole inside the accretion disks. And this is an Event Horizon Telescope collaboration, so which observed a supermassive black hole in the center of the M87 galaxy. It's roughly 50 billion light years away. And it was known that for a long time that there should be a supermassive black hole, but then they managed actually to see the black hole. So this is a black spot, so and this is a black hole. And this was a complicated project, including telescopes on radio telescopes on several continents. And so the mass of this black hole is roughly 6 billions of solar masses. Next, I think the best evidence is the gravitational waves. So the gravitational waves were discovered directly for the first time 5 years ago. And they saw the pulse, the wave pulse produced by the merging of two black holes with the masses of roughly 36 and 29 solar masses at the distance of more than 1 billion light years away. So these black holes were two black holes formed a bound system, and they were spirally inside until they merged, and only one single black hole arose. And a considerable amount of energy was emitted in the form of gravity radiation, amount about 3 solar masses. And when they measured the spectra of the signal, they discovered identical coincidence with the spectrum obtained in the numerically. So numerical calculations give exactly the same result. And so this, I think, this is the most convincing evidence in favor of black holes, and this is the Nobel Prize in physics 3 years ago. And finally, second half of Nobel Prize was shared between two groups, American group and the German group, who were monitoring a supermassive black hole in the center of Milky Way. So it was also known for a long time that there should be a black hole there. But the problem is that the center of Milky Way is hidden from us by a dust clouds, and it's not visible, not directly visible. And it can only be observed in the infrared. And then there is a source of gamma rays, which normally emits in the radio spectrum, but from time to time, it gives so there is a source of radio waves. And then sometimes the radio waves become gamma rays. And then the interpretation is that there is a black hole which absorbs gas, but from time to time, there are heavy bodies like asteroids which fall inside, and this gives gamma ray bursts. So it was known, and but the black hole was not directly seen. And what they did was this: the black hole is somewhere in the center, but there are normal stars orbiting around. And then they were tracing orbits of roughly 90 stars over something like 15 years, measuring their positions and in order to determine the periods and then the orbits, size of the orbits. And then they simply applied the Kepler law, third Kepler law, to calculate the mass of the central object, which is roughly 2 million solar masses, which is not a lot. 2 million is not a lot. But the region where the mass is confined is so small that any other explanations other than black holes are excluded. And this gives us, and this corresponds to closest to us supermassive black hole. And finally, this is a lot like last slide. Just some questions. How are black hole formed? Well, either by collapse or collapse of stars, or by collapse of fluctuations in primordial plasma, because it's possible that even before the usual stars were formed, these fluctuations segregated by gravity force into pieces which collapsed, which never burned. And then black holes can absorb the outside, the surrounding matter and increasing their size. But it's a slow, relatively slow process. Now, the question is, how are supermassive black holes are formed? The masses of billions of solar masses. And in fact, it's a puzzle. At the moment, nobody knows. So there are several hypotheses. And then probably they are already born, were already born supermassive at the very beginning. How many black holes are around? Many, a lot. So apparently, a considerable part of matter should be in the black hole form. And then some people think that perhaps the dark matter is made of black holes. The last question: are black holes dangerous? No, because they are detected simply by gravity fields, and they're not more dangerous than ordinary celestial bodies, unless you jump inside. And if one imagine a black hole with the mass of asteroid passing through the Earth, nobody would notice. Okay, this is my last slide. So I am something like 15 minutes outside the schedule. So thank you. This is all I wanted to tell you. Maybe there are questions, but I do not understand how these questions can be asked.
So we'll ask on the students' behalf. Okay. So
Okay.
Yeah. So thank you, Professor Volkov, for such a wonderful and exhaustive interaction with our students, and it was a very wonderful experience. And I hope that most of the students, they will take away many things from your lecture, and it is a part of their theory classes also. So this was an exhaustive approach about this black hole journey and all those gravitational. So we have a lot of questions from the students' end, because it was also live on YouTube, this channel of Shulin University. So we had a lot of questions on this platform, Zoom platform, as well as on that YouTube channel also. So to just have a I have just requested my colleague, Dr. Anirban, for asking 2-3 very, I would say, those important questions, and then we can share those questions through mail with you, and then we can answer to the students if possible. So, Dr. Anirban, I hope that you have compiled.
yes, yes,
Yeah.
yes.
So please.
So the first question means was about the evidence of this black hole. So it was already answered, I guess. So everybody knows that we have now the picture of a black hole. So one question was about the evidence of white holes. What should we expect?
White holes? No,
Yeah.
no. There are no white holes.
Yeah.
So
white
holes
dwarfs.
are white dwarfs.
Yes.
White dwarfs. But this is not even physics. This is astronomy.
Yeah.
And then this is something completely trivial. And then one should be, so there are billions and billions. So all stars over modest masses, they end up in a white dwarf state. And in astronomy, there is a so-called Gershsprung-Russell diagram, and then the dependence of mass on the luminosity, and then there are facts about. It's really a rather astronomical question, but the astronomers, so for them this is something completely trivial. So there are many. So again, I think closest to our planet is a Sirius B. It was discovered by Bessel, by the way. Bessel worked in the middle of 19th century. So already at that time, it was known that, well, they discovered that the trajectory of Sirius is not straight. The Sirius slightly oscillates because it is because the component of the binary pair, and it oscillates around the common center of mass. And then the second component is invisible at that time, but nowadays I suppose it can be visible. It can be seen in a sufficiently large telescope. So white dwarfs these are not black holes. This is something simple.
Yeah. So about the time in event horizon, I think it was answered by you very nicely. One question was about the dimension of A in 2011 Nobel Prize. So you do not have the slides number with you. So if you go back to the slides on 2011 Nobel Prize.
Yeah, this okay. I understand. So this is cosmology.
Yes.
This I was talking about cosmology, and this is just a moment. It's here, yeah.
Yeah. So what is the dimension of A, and how does it relate to dark matter?
Okay, dimension of what?
A. The A dot square by A square, right? So in this equation.
A
yes,
is
yes.
yeah. I see. A is if you like, it's a dimensionless. So it depends. So you can either assume the coordinates x, y, z to be dimensional full, then A will be dimensionless, or you can normalize them in some using some scale. Then A will be dimension full, but in the ratio A dot over A, there is no dimension. So the dimension of the left hand side is 1 over t squared. because dot squared.
Yeah.
And then the dimension of the right hand is also 1 over t squared,
Yes.
because g times rho has a dimension of precisely of 1 over t squared.
1 over t squared.
Precisely, yeah.
So there is evidence that this dark matter is made up of with black holes.
Yes. Well, there are many models. So dark matter is something which clusterizes.
Yeah.
So which something which is which tends to approach the gravitating center, and then every galaxy is surrounded by a cloud of dark matter, whose total mass is 5 times as large as the visible mass. And then there are effectively models that this could be either black holes or cold white dwarfs, sometimes called brown Jupiters, because Jupiter is the objects of the size of Jupiter. There are, but you see, there are many models on the market at the moment. Nobody knows what dark matter is.
Yes.
And this is one of the models.
Yeah.
And so people think that maybe there are some primordial black holes formed at the early stages of cosmological evolutions, which make this dark small dark matter. Okay.
Maybe one last question. So can black holes get smaller in size with time, or means what are the dynamics of these black holes?
Small in size, yes. The only process, this is the Hawking process.
Yeah.
So this is the famous. This is famous because it gives connection with quantum gravity. So according to Hawking, black holes can evaporate. And for usual black holes, for example, if you take a smaller mass black hole, you see this is the temperature is 10 to the minus 8 Kelvin, and this is which is extremely small, and then you can forget about it. But if you take a black hole of the size of asteroid, then this temperature will be already high enough. And so the black hole of the asteroid size is microscopically small. I think it's smaller than an atom. It will carry the asteroid mass inside, and when it evaporates, when it gets smaller, the temperature goes higher, and then therefore, but the evaporation rate is proportional to the 4th power of temperature, and then therefore the evaporation rate will increase enormously during the last moments, and so which means that the small black holes should explode in a flash, like a bomb, and this produces the fundamental paradox. The paradox is that if they explode, they should go into the thermal radiation, and then the question is what happens to the information, because the black holes are formed by a collapse of stars, and then the collapsing matter carried some information with it, and then this information apparently disappears after the collapse and after explosion. And from the physical point of view, this means that the physical evolution is not unitary, which means that the probability is not conserved. And so this was a fundamental question of Hawking: if gravity preserves unitarity of the evolution, and this question still has no answer. So this is one of the fundamental questions of modern physics. So this evaporation of black holes and relation to quantum mechanics.
Yes, so I think all of the main questions was answered. So I think yes, yes. Go ahead.
Yeah.
Good evening, sir. This is Dr. Kumar.
Okay. Evening.
Sir, you in the last slide you mentioned that the black holes, they are surrounded by nearly 90 stars,
Yes.
right?
I think more than 90, but
More than 90. Okay.
I think they mentioned in their paper
Yes,
90
yes.
stars.
90, nearly 90 ordinary small stars. Is it right?
Yeah, yeah, right. Yes.
So,
yes.
sir, after they die,
The stars,
as they die, they will collapse to the they will merge into the surrounding black hole.
not at all. No.
What
These
happens
stars,
after their death? What happens there after their death? After
they will
converted
continue.
into mass totally.
They will be continue to orbit the central black hole. So each of the stars is an ordinary star,
Okay.
and it lives its individual life. Depending on its mass, it can collapse or it can become a white dwarf or neutron star. But it will continue to make revolutions around black holes, because you see it's not easy to fall inside.
Okay.
Because there is energy conservation and angular momentum conservation.
Okay.
And in order to fall inside, it should lose its energy. Therefore, if there is some extra interaction, unless there is extra interaction or collision or whatever, all the stars will forever orbit the central black hole forever, unless there is some perturbation.
Okay.
Because again, falling into a black hole is not easy; it's complicated because of the conservation of energy and the conservation of angular momentum.
Yeah. And sir, in the last, what can we expect after black hole? What can we expect the bigger object, astronomical object?
Bigger than what?
After black hole?
I don't understand. What do you mean by after black hole?
After means the bigger than this, or
is there anything bigger than the black holes?
Yes. What can we expect in near future?
No.
Which is hidden to us, or anyway greater than black hole, like this?
No. I still don't very good.
Can we expect bigger than this?
A black hole bigger than this supermassive? No. Apparently, black holes have no upper limit, so they can increase their size infinitely. So if they have an infinite amount of matter to absorb, they will increase their size infinitely. But fortunately, the black holes are only able to swallow the matter which is around in the galaxy, and then they're starving.
Yes. Then the new thing will be born.
Starving black holes. They will not absorb anything. But there is no upper limit, so they can absorb as much as there is around. So in principle, they can absorb the whole universe.
Yes.
Yeah.
Thank you.
Okay, I think we are done with all the questions. So I think we can conclude now. So Dr. Rajesh.
As already shared, that it was a wonderful interaction, sir, and we will love to have you if you can spare a bit time, because it was a very knowledgeable. The questions are showing in the chat box and on YouTube channel. We will share the link with you also, that YouTube channel and questions. And it was wonderful to have you today. And this is one of the part of our science web series, which we have started here in Shulin University for the students from sciences background. And definitely the speakers of your stature, they are definitely adding the values to the knowledge which the students are carrying right now, and they will definitely get benefit out of it, not only in their this text knowledge, but in their competitive those examinations also. So I am extremely, and on behalf of Shulin University and on my own school faculty members, I am very, very thankful to you. And now I will request my colleague Dr. Pavan Kumar Sharma for vote of thanks.
Thank you, Dean sir, Professor Rajesh sir. So good evening all. This is Dr. Pawan Kumar from Shul University. It was really a highly bright and wonderful talk on black hole by Professor Mikhail Volkov from University of Tours, France. So really it was amazing, wonderful. So on behalf of School of Physics and Materials Science, Honorable Vice Chancellor Professor P.K. Khosla, Honorable Registrar Sir, all deans, all faculty members, all staff members, all students and young researchers of Shul University, and nevertheless some young minds, principals, teachers from various institutes of Northern India, we all extend our heartiest thanks to you, sir, Honorable Professor Mikhail Volkov, sir. We are really thankful to you for sparing your valuable time to us. And I am really thankful to you, sir. And I wish you good health in future. And I wish that you will be a part of our web series in future also, because we are going to constitute astronomical club in our Shul University very soon. So I hope that you will be the part of that in our coming programs also. So thank you, sir. A lot of thanks from India. Jai Hind, sir. Thank you.
Okay, thank you. Thank you for your kind words. Thank you for listening. Thank you for inviting me.